All right, so in this video, we are going to be looking at how can we go about evaluating logarithms. So just like I can say 2 plus 3 equals 5, or I know that 2 times 3 equals 6, and I know that 2 to the third equals 8. All of these are evaluating an operation, so addition, multiplication, exponent. Just like that, I can evaluate all of these to get a final number, such as 5, 6, or 8. So in order to do that, we might need a quick reminder of, well, what even is a logarithm? So a logarithm is another way that we rewrite an exponential, or it is the inverse of an exponential, in fact. So one of the big things that we like to show is that the output of the logarithm is equal to the exponent of the exponential. So I kind of like to say this, that taking a logarithm is answering the question, what was the exponent? What exponent turned your base into your argument? Because that's what we're doing here. What exponent takes b and creates a? So b to the what equals a. That's what we're seeing here. B to the what equals a. So for each of these, we can quickly ask ourselves that. We're saying 3 to the what equals 27. Well, 3 cubed. So the answer here is 3. 2 to the what equals 16. Well, I know 2 to the fourth equals 16, so this one's equal to 4. I like this relationship here. These ones are very similar to each other. We're asking 4 to the what is equal to 16, while 4 squared is equal to 16. So notice how we're just going through and we're saying, what was the exponent that made this statement true? 2 to the what gave me 16, 2 to the fourth. As we get to the second row, though, I start to see some interesting things. I'm still saying 125 to the what equals 5. I have to think a little bit more critically about this. And I know that the cubed root of 125 is equal to 5. And the cube root written as an exponent is 1/3. So therefore, this is 1/3. So that's kind of cool. When my argument was smaller than my base, my exponent was a fraction. That's looking at that radical or root relationship here. But for this one, I now have an argument that's a fraction. So I'm saying 6 to the what equals 1 over 216. Well, I know in order for a fraction to be created using an exponent, I have to have a negative exponent. And to make 6 into 216, I have to multiply it 3 times. So the exponent here was negative 3. I get stuck here looking, I don't see a base. So I'm actually just going to highlight this one and we're going to come back to it because without the base, I don't know what I'm taking to get to 100. So that one leaves me a little stuck. I'm going to come back. Oh, coming here. Okay. 8 to the what equals 8? Well, just 1. This one is an identity or a property. Every time this is going to happen because the only thing you can raise something to get it to become itself is 1. This will always be true. It's pretty cool. This one's another fun one. 5 to the what equals 1? Well, the only way to take something and turn it into 1 using an exponent is 0. So anytime your argument is 0, I'm sorry, I just said that wrong. Anytime your argument is 1, your final answer, your output, your exponent will always be 0. This one stumps me again. I haven't seen one that is an ln. So just like the other one, we're going to have to take a moment back. So most of these were pretty easy to do. We are just asking ourselves, what was the exponent? And those are what they were evaluating to. These two show us that there's something else going on here. And so there's actually two very special types of logarithms that we can look at. And notice it's the ln, which is what we just saw on the other page. We had the ln of 2. And log without a base. So these two special types of logarithms, there's kind of two reasons that we use them. One, calculators have these. So not every calculator has the ability to type in a log with a different base. Newer calculators these days do, which is pretty cool, but not every single one of them do. And so therefore, there are these two really, really common types of logarithms that we see the most. The first one is the natural log. So natural log NL here. And notice that we write this LN. So instead of writing the word log, we write LN, and that's going to represent the natural log. A natural log has a base of E. Now, E is a special number. It is Euler's number. And just kind of like how pi is a special number, E is also a special number. So it is a variable, so we represent it with E, but it represents the same number always. And that number is approximately 2.7. Just like we represent pi as 3.14, we know that is an irrational number that goes on, so does Euler's number, but we're going to leave it here at 2.7. In fact, you don't even need to know that because in reality, we're always just going to leave it as E, but I'd like you to know that it does represent a very specific number. This number is a really, really cool number that makes continuous compounding work. So it makes populations that are constantly growing at a certain rate based off of that new growth. It's that special number, it makes it work. And so therefore we use this a lot in natural situations. That's why it's called a natural log. So here, there's a ton of science applications that use these. But once again, the really cool thing is if you just see the ln, that means that the base was originally E. So you can see this rewrite here. If I see E, I know that typically I'm going to start by writing the word log. But as soon as I see E as my ace, I go, nope, I'm going to write ln. Once again, the exponent is still the output. And what was the output is still the inside. And you can see that here as well. So anytime we see ln, we know that the base is actually an E. The other most common one here is well called the common log. Its base is 10. So if you think about it, if I have x, just x, you know two things. You know that it's to the first power and that the coefficient is 1. We don't write the first power, nor do we write a coefficient of 1. Those are implied. The same thing is true with a common log. Another example is if I did this, you know that I was asking you for the square root of 4, which is 2. If it's a different type of root, we would add that index. In the world of logarithms, if we don't have a base written, it's a base of 10. And that's because we have a base 10 number system. So when we hit 10, we start over. So because we have a base 10 number system, this is our common log. This is our basic one that we go back to each time. So now that I've looked at these, I can actually come back to two of these original ones that we left. So here, as soon as I see that there's not a base, I go, oh, actually there was a 10 there. So I'm saying 10 to the what equals 100. Well, the 10 ones are really cool, and it's how many zeros do you have? So I have 2 zeros, so 2. 10 squared equals 100. This one here, I see that it's E, so it's asking me E to the what equals 2. Unfortunately, I don't know what that number is. So this one is unsolvable without a calculator. Now, it is solvable if you have a calculator, but without a calculator, at this point, it's going to be unsolvable. So the last thing that we can kind of do in this idea of evaluating is what happens when they're in a whole expression together. So if we look here, this is a similar idea of saying like 2 times 3 plus 5 minus 6 plus 10. Now, those aren't going to be the same numbers, but it's the same idea as having operations inside of operations. So if I'm asked to evaluate something like this, I can evaluate each individual one. So log base 2 of 8 is saying what was the exponent that turned 2 into 8? That's 3. Plus log base 5 of 125. Well, I know once again, in order to create this fraction, it had to be negative, and 5 squared is 25, so that's mean negative 2. We just did this one on the other page. It was also 2, and I'm just bringing that negative with me. So now I have 3 minus 2 minus 2, which is equal to negative 1. So even though this looks like a kind of scary expression to look at, it actually simplifies down to just -1.